So we are looking here at where we left last Thursday after we modeled the problem that we did using the finite element method, the classical method of two bars connected together, A, B, B, C, where we had a 1,000 pounds applied at B. A is fixed and B has a prescribed displacement of 0.002 inch. And we prepared the model. We had a part. We created the material. We used the cross section that we define in design modeler, circular 1 and circular 2. We used the automatic mesh generator to create our mesh. We did set up the loads and constraints. So when you look here, I have a fixed support at A. I have a prescribed displacement of 0.002 inch at C. And I have this 1,000 pound force applied at B. So once everything was done, we click solve and we were able to run the analysis, but we didn't have any results. So then we went to solution and started defining the results we want to look at. The first thing I typically like to check is to see whether my part is behaving as expected or not. So we started looking at the total deformation, and I can also play the animation. And I see that my parts are moving to the right. And yes, I get the 0.002, the prescribed at the right end. But when I looked carefully at the center where the maximum displacement, the red, occurs, I'm only seeing 0.0026. From our prior knowledge, because we solved this by hand, we know that this number is not correct. And we were getting about 0.005 of an inch at point B. So we know that something was wrong. And we did some troubleshooting, but I continued that. And I found that definitely this had to do with the material that was not assigned correctly. So I went back and I looked, and I do have the class example material. I have the default structure steel and structure steel 2. And when I went to my part, in the details of the part, I see here that the assignment went to structure steel and not to the class material that we defined. And this affected our results. So how do we change that? And this actually, every time you are using beam elements, you want to make sure you go within ANSYS structure and make sure you assign the material that you created in Workbench to your part or your model. So this is where we attach the material to the part. So when I come here and change my assignment to the class example material, all my results are going to be gone. You see this yellow flash icons indicating that there is work needs to be done. So when I come back and click solve, is rerunning the numbers, and I have all check marks, green check marks, indicating that we do have an answer and it's all done. So now if I go to my total deformation again and look at it this time, I see that the red now is 0.00555 as we expected. If I play the animation, still doing what we expect, and everything looks good. Now I can look at the force reaction, which we found earlier to be 555. Let's look at ANSYS. I'm getting 555.47. When we work this by hand, we got 555.56, right? So you see, there is a small percent error, but it's very acceptable if you look at the percent error. Do we always expect a percent error? Yes. When we're using the finite element method, it's a numerical method. There are approximations that are undertaken. And with all the numerical manipulations that are being done, this mathematical error may increase, but we want to make sure that it is within acceptable limits. In other words, that we have a fine enough mesh to the extent that the solution is converging, is getting as close as possible to the exact solution. I look at the forced reaction to the right, and I'm getting 444.53. And just a reminder, the reactions here, we were able to define using the probes. So we used probe, and I picked the force reaction. Since this is an axially loaded part, we are not expecting any moment reaction. That's why we do not have a probe for a moment reaction. But should we do that, and I use it, I put a probe here on the fixed displacement for a moment reaction, I should get a 0. So let's try it. I created here a moment reaction at the fixed support, and I go like solve. And I go down here, and you see all zeros. Okay, these are two force members. We also defined a deformation probe to report the deformation exactly at point B. And when I come here, I find that I got 0.005559, which when we worked it by hand, we also got this 0.005556. So again, this is very close. The last thing that we did on, was to look at the stresses using the beam tool. And because these are axially loaded parts, the axial stress is all coming from the normal force. I do not get any axial bending stress. So when I look at direct stress, you see now I am showing that member AB is in tension, it's positive, it's all red, and the normal force is 5,559. I'm sorry, the axial stress, not the normal force. It is in tension, and the axial stress is 5,559 psi. When I look at the member BC, it is in compression, and the axial stress is 2,966 almost psi. Okay. So this was everything that was required for the example problem that we solved earlier. So we were able to solve this problem using the compatibility equations of equilibrium, like you did in solids. We solved it using the finite element process, and we also solved it using ANSYS. And we want to do more of that as we move forward, so we can become better users of ANSYS. We want to solve more problems similar to the ones that you did by hand. So you're going to start noticing that the homework assignments are going to ask you to redo some of the problems we did earlier in the class using ANSYS Workbench. Like homework 5 is exactly the same as homework 4 that you did by hand, but you're going to work it using ANSYS Workbench and using beam elements. So you're just going to be creating these lines, material, meshing it, apply the loads and constraints, and do exactly the same like we did for this example. Any questions so far?
For homework 5, it'd be acceptable to just use like the automatic mesh.
Correct. Yeah. So for the most part in this class, we want to use the automatic mesh generator, right? If you're becoming like an experienced user of ANSYS, you really want to edit the mesh. And this is something we can sure do in ANSYS. You see here, mesh, I can control the sizing, I can use face meshing, I can copy a mesh, I can use match control. So there are controls that help you choose how fine or how you want your mesh to look like if you want to do that. I want to remind you that the element that we are using here is a beam element. A beam element is not a bar element. So this element is capable of allowing an axial force, axial displacement, is also allows for rotation and bending, as well as shear. So we can use the same methodology to model beams in bending, as well as shafts in torsion. So this allows me to model a beam or a shaft. So we want to take this a next step and use ANSYS to model a beam and find some results. All right. So first thing I'm going to do here after we fix that, I am going to save. So I'm going to come here and say, save the project. And if I take you back to Workbench, I only have the static structure analysis. I deleted everything else that we didn't need because we were simply doing a static structure analysis. So just to keep things simple, I am going to continue to use these two bars, AB and BC. And remember, in ANSYS, we modeled these using 2 line concepts and 3 points. Originally, we had the 1000 Newton along the axis, and this was fixed, and we had this prescribed displacement at C. Now, today, I'm going to look at this as a simply supported beam. And I'm going to put a load at point B. So we're going to use the same geometry, but we'll use different type of supports. And you can see clearly a difference between a beam and a 2-force member. A beam is loaded by a transverse load perpendicular to its axis. So if this is the axis of the beam along X, I have the force acting in the Y direction, and it's in the negative Y direction. And we are working in 3D, so this is my Z direction. I will remind you that the dimensions, this was 10 inches and this was 12 inches. AB, we modeled this using circular sections. So we had the circular 1 and circular 2. The area of AB was equal to 0.1 square inch, and the area of BC was equal to 0.15 square inch. Both of them are circular sections. And let's apply here a load of 100 pounds. If I look at this simply supported beam, it's a determinate problem, meaning I can simply use equations of equilibrium to solve for the unknown support reactions, I can find RA, I can find RC, and we know that here this is a roller that allows only displacement along the x-axis, but really we shouldn't get much. And after finding the support reactions, what we typically did in statics and in solids and in machine design was to draw the shear and moment diagram. So I can come here and say I'm going to draw the shear diagram where I have this RA. So I go up, I go straight, I come here to the 100, and I go down 100. I go straight all the way to C because I don't have any distributed loads, and up back to 0. So this was my shear diagram. And for my moment, if I have here positive shear, I have here negative. This is constant, so I have a constant slope. So this is the moment diagram. And here I also have a constant negative slope that takes me back to 0. So my moment diagram would look like something like this. I also expect that as this beam is loaded with 100 pounds, that it is going to deform, and I'm going to get an elastic curve that looks something like this. And please note this beam is not symmetric because it's 10 and 12 and 2 different cross-sectional areas. So what we want to do now is to use ANSYS to solve this beam problem. Are you all following with me? Knowing that we've already solved this geometry or this model for an axial force, I can reuse the model and only change the setup, right? So I'm going to go back to Workbench and define a new static structural analysis. So from analysis systems, I'm going to go to static structural. I'm going to select it and grab it such that I am reusing the model. So I can come here with this static structure. I can call this one axially loaded. And I can come to this one and change its name, rename it, and call it beam in bending. Oh, I selected the static structural from my toolbox, like here, and I grab it, and I took it all the way to model. Okay. Within my project schematic. Right click and delete. So I can come here, like right click like this and choose to delete. Okay, you don't need to delete them. I just want to make sure no one is confused. But for now, I want you to focus and continue working with me, right? Oops. So now if I go to the beam and bending and double click the model, what's this? If I double click on the model, I think I need to double click setup, not model, because the model is just copied over. So we're not changing the model, but we are changing the setup. So here, this is launching. And please do not get confused because it's still keeping the first static structure with its loads and solution. They're overlapping here. And then here is static structure 2, the new one that we want to define. So when I go to static structure here, I get to define my supports. And I want to make sure I can see my points. So I'm going to go to display. And I want to select show vertices. So now I can see my points. I go back to static structure 2, which by the way, I can come here and rename it as beam in bending. And the top one, I'm going to rename it to axially loaded. Okay. So we have axially loaded and beam in bending. So I'm going to go to beam in bending, and I want to define my supports, which I have a pin support to the left and a roller support to the right. So we need to understand in terms of degrees of freedom, what does a pin support do? See, degrees of freedom, when this beam is going to move in the XY plane, this pin is not going to allow point A to translate in X. It's not going to allow it to translate in Y. For our problem, we don't have a third dimension. So really also is not going to allow it to move in the Z. Now, because these are beam elements, when the beam bends, the section is rotating about the Z axis. So every time I'm using beam elements, I need to consider 3 translational degrees of freedom and 3 rotational degrees of freedom. So I can come here and say that the pin support is going to restrain all 3 translational degrees of freedom, but is gonna allow rotation, so free all 3 rotational degrees of freedom. That's what my pin support is doing. Okay, how about the roller? Is going to restrain translation perpendicular to the plane shown, right? As a matter of fact, if I look at this one, because my problem is really defined in the XY plane, it is really only free in the direction of the rollers, you see, for translation. So I can say here free translation degree of freedom in the direction of the rollers. In this case, it's going to be X, right? Here is going to be X direction. How about rotations? Is free in all 3 rotational degrees of freedom. For this problem, I don't have a fixed support. But what would a fixed support do? And so a fixed support, like when we have a cantilever, basically it prevents, it's like a wall, like attaching something to the wall. So it cannot translate and it cannot rotate in all 6 degrees of freedom. So that's a fixed support. So it's important to understand what is it that you are trying to model. When we are using ANSYS, we're trying to run computer simulation. Okay, and this is always going to be a very important step, like choosing the correct element to have the right mesh. Then making sure you apply correct boundary condition, because it's very easy for me to put like a fixed support here and a fixed support here, and I'm going to be solving a beam, but I'm not going to get this behavior. Okay, is that clear? Okay, so let's go back to ANSYS. You can go to mechanical. And I am looking here at the beam in bending analysis setting. I'm going to go to the environment where I can define my supports. And you look here, we have supports. If you click on it, you have several types of supports, including fixed. And there is something in ANSYS called simply supported. Insert a simply supported object, 3D only, prevent one or more straight or curved edges or vertex or vertices from moving or deforming. But look what it says at the end, rotations are allowed, which is what's gonna give me a behavior of a pin support. Is that clear? So now I can use the simply supported option and apply it to point A. So click point A and go say apply. So this gives me a simple support for the pin support. Now for this particular problem, can I use a simple support at C? Yeah. Is it going to be exactly modeling what I want to capture? For this particular loading, yes. But for other types of loading, no. So I want to take this opportunity and show you how to create a pin support rather than just simply throwing in a pin support, a simple support, right? So with our understanding of a pin support, I am going to insert or define a support that is called displacement. So I'm going to select this displacement and apply it to the vertex to the right and go apply. And I'm going to look here at the details of displacement. Okay, this displacement constraint affects only translational degrees of freedom in X, Y, and Z. And based on our good understanding of the roller support, we know that this roller support is going to constrain translation in Y and in Z and only allow for X. So I'm going to go back to mechanical, and I am going to let the X component to be free and make sure to put a 0 in the Y and a 0 in the Z. So this is how I model my roller support that is allowing translation in the X direction. Okay, so these are boundary conditions. Next, I go to loads. And we have a simple force. So I can come here, select a force applied on the vertex. I picked the edge by mistake. That's not what I want to do. So I want to make sure that I pick my vertex. Do not pick the edge. If you pick the edge, ANSYS will distribute the load uniformly over the edge, which is another good feature. We can use it should we have a distributed load. But now we know, and by the way, the results are very different. So now I want to make sure the load is applied to the vertex. I go apply, and I'm going to define this force using components. So type here is a force defined by, and instead of a vector, I'm going to use components. And now I'm looking at X, Y, and Z components. My force is acting vertically downward, so it's a Y component. And I'm going to put a minus 100. Enter. And you see the icon is showing me the direction of my force. So now we have this beam in bending with 2 supports and 1 load. We are ready to see whether we have a solution or not. A warning. If I'm going to work this problem by hand, I know that I'm working in the XY plane. ANSYS works in 3D. So solving a 3D problem. If I try to run it like this, it is going to fail. Did I do anything wrong? If I'm working in plane, no, I didn't. But because ANSYS is thinking 3D, is want to make sure that rigid body motion is prevented in all 6 degrees of freedom. Now I know with these type of supports, my beam is not going to translate in X, is not going to move in Y, is not going to move in Z. Okay. Now this beam cannot rotate about the Z axis, cannot rotate about the Y axis because it's being held. But how about rotating about the X axis with these type of supports? The beam, as we defined it, can spin about its axis. And this is something we need to prevent. Now, I do not have any torque applied. So we need to have like a workaround. Really, we do not have anything to prevent the beam from rotation. We know it's not going to rotate. But numerically, we want to add a virtual support. Should there be any torque, it's going to prevent the beam from spinning. Okay. In order to demonstrate this, let me try to run this problem here and see what we're going to get. Warning, solver pivot warnings. And I get an error because there are rigid body motion. I get this red icon meaning the solution failed. Simple fix. I'm going to go back to my beam in bending and I'm going to come and add not a fixed support, but if I go here under supports, there is something called fixed rotation. I do not want to fix all 3 degrees of freedom. This is very important. A quick fix that you're going to give you very wrong answers is to put fixed rotation everywhere. But we want to specifically prevent the beam from spinning about the x-axis. So yes, I can use fixed rotation, and I'm going to apply it to the end, not to interfere with what's happening. And I do not want it to be fixed about X, Y, and Z, but only want to fix it about X. I want to make sure I have to set this free, and I have to set the Z rotation free. Otherwise, I'm going to get a wrong answer. I select my external vertex here. So now we added this fixed rotation only about the x-axis. I can only define this correctly if I understand degrees of freedom and what is it that I want to accomplish.
Why did you choose the fixed rotation at that point?
I could as well do it on the other right end, but I would not do it at the center because I do not want it to interfere with what's happening along the length of the beam. Now, let me tell you, and we're going to prove that. After we solve the beam, I'm going to come back and check and see what is this fixed rotation doing? What do you guess is going to be doing? How much reaction we're going to see from this support? Perfect zero? Almost a zero, right? Any numerical errors could happen. Well, really, this support is doing nothing. Is that the numerically, ANSYS see that there is a solution to this problem. Is that clear? Okay. Let's now try to solve. solving the mathematical model, green check mark. So that fixed our problem. Did you all get it? Next, we want to start looking at results. I'm going to go to my solution and start defining results. The first thing I like to look at, again, is deformation. Total deformation is fine. So I'm going to solve here for deformation and look at what our beam is doing. Is this what we expected? I can even play the animation. As the beam gets loading, it's going in bending. I want you to pay attention to the rotational degrees of freedom at the two ends. You see, the beam is free to rotate. If I use fixed support, I won't get that behavior. That's why I always like to checking here the behavior. Is this what I expect my beam to be doing? Next, I want to look at support reactions. So I'm going to go to solution, probe, and I'm going to look at a force reaction, and I'm going to select the simple support. I'm going to go to probe and force reaction, and now I'm going to select the displacement. So I'm looking at A and B. And we should only get components in the y direction. So I'm going to solve for these. And I'm going to look at the force to the right, going up as I expected, and look at the components. I'm getting 54.545 pounds upwards, which is what we would expect because the 100 pounds is applied closer to the right end. So A gets the bigger portion. Now, before looking at B, at the support at C, we're looking now at 45.4, right? So go to reaction here, 45.4. So this is how the numbers should make sense to us. When we solved for beams, we are interested in internal forces or stresses. I want to show you here, when you are using beams, if you go to results, you will find that stresses are all grayed out, because I'm not using any solid elements. If I really want to look at stresses like we did with the axially loaded problem, I will go to beam results. I will go to toolbox and select the beam tool. The beam tool would allow me to look at stresses from a normal force as well as stresses, combined stresses, or I can come here and say insert beam tool stress and choose specifically like maximum bending stress. Why is there a max and a min? What happens with bending? We get both tension and compression, right? So I get a maximum positive and a minimum compression. So I can look at both. For this problem, we expect them to be the same magnitude, opposite and equal. But I really wanted to show you, when I solve for this, that the direct stress should be a perfect zero because I don't have any normal force. So when I come here and look at direct stress, yeah, the beam is bending, but I don't get any normal stress. If I look at the bending stress, I'm looking here at the maximum, so they're all positive. And you see here, I'm getting a 122,000 PSI. Positive. Remember this number, 122,000 PSI. Now, if I look at the combined stress, what should I get? Direct was 0, bending is 122,000. When you look at the combined, you're adding the two together. So I should still get 122. Okay, so if I go to the maximum combined, I get this. It is very important to understand what we're doing. Okay. What do these directs and bending stress really mean? the direct stress, and we're looking at a sigma here. This is calculated using the normal force divided by the area. A bending stress sigma is calculated from the bending, which is the minus mz over iz times y. It could also be from an my. So I could have the my over iy times z by axial bending, like you did in solids. If I call this sigma 1 and sigma 2, the combined stress, sigma 3, is equal to sigma 1 plus sigma 2. So this is why when sigma 1 was a 0, the combined stress was the same as the bending stress. So is the concept clear? So I'm going to go back to mechanical. And the last thing we want to do before we leave is to look at shear and bending diagrams, as well as a displacement or deflection curve. How do I do that? We always, when we do it by hand, go from the left to the right. In ANSYS, I first need to define, if I come here and go to solution and go to beam results diagram, I can look at a bending moment. I can look at an axial force. I can look at a torsional moment. But I can also do shear and moment diagrams. If I want to do shear and moment diagrams, it's going to ask me for a path. So I need first to define a path to let ANSYS know where do you want to plot, or what entries, what components do you want to use for this shear and moment diagrams. How do I create a path? I go all the way up to my model. I go insert and I choose construction geometry and choose a path. So you see here, I'm going to the model, insert, construction geometry, and I select a path. And it says here, insert a path object represent a spatial curve to which you scope the results. So I go path, and you want to make sure to define your path not using points, but using edges. So I come here and select edge. And now my path is going to be using AB, and then control bottom, I want to select also BC. So this is my selected path. I go apply. You see here I have point 1 and 2 for my path. If I go down to my total shear and moment diagram, now I can select my path that we defined. And we want to look at, I can look at the total shear and moment. Really what we are looking at is not the total, but rather we want to look at what's happening in the XY plane. So I should come here and select really VY and MZ. But I have to warn you that there is a bug in ANSYS, and sometimes it switches the two planes. So you want to use your common sense, making sure you're looking at the correct one. So let's start here by trying VY, MZ. And let's try to solve and see what we're going to get. I'm getting here the shear force, yes, is going downwards instead of upwards as we expect, but it is what we expect for a shear moment diagram, a shear diagram. Look at the moment here. I'm getting the maximum moment I expect. And look at this blue curve. This is my elastic curve or displacement function. You remember when we were working on shafts and we had to go to the appendix to look at equations of elastic curve to solve for displacements? Now, ANSYS can plot that curve specific to my problem. When we did stepped shaft, I told you we're not going to do deflections by hand. This is where we can do deflections using ANSYS. So for this problem, I was able to plot shear diagram, moment diagram, as well as the displacement diagram. We have 1 more minute left. And the one last thing I want to leave you with is when you're working on shafts problems, we have bearings. What do the bearings do?
They allow it to rotate on axis.
Correct. They allow it to rotate, they allow it to spin, but they do not allow it to translate. So when you're trying to model a shaft, we can use, for the bearings, I can use simple supports and apply it to the vertex. So we're going to use center line to center line direction. I'm saying that for those of you who are going to start working on homework number 6, yeah, shaft problems. The other thing you're going to do for shafts is when you are looking at the shaft, in addition to the forces, you also have torques. What is the torque? So I do not need to include the pulley in my model. I'm going to have a beam like looks like this. A torque is a bending, is a moment about the x-axis. So if I want to do that, I can come here and go to a moment, select the point where the moment is applied, and I want to make sure to come here to the components, define the moment using components, and define my bending moment about the x-axis. This will show like shaft. So if I come here and say apply, I want you to look here at this. You see how the moment is applied? So this is how you're going to apply a torque in your shaft. With this being said, you can complete homework 5 as well as homework 6. At least, please make sure before you come on Thursday, you have started the models for homework 6, because on the Thursday, we're going to have like a workshop. I'm going to be around and answer questions specific to your work. So get your problems ready and your questions ready for Thursday. Okay, I'll see you all on Thursday. Thank you.
I was just asking about the part about what he was before. And so it's a Shear. He said
Time.